Hey guys! Alright, we're going to continue on our lecture of Chapter 9. Let's go ahead and review what we know so far. I changed that on the notes already, I hope. About eliminations with alcohol. So we already knew how to do eliminations with alcohol halides. Eliminations with alcohol is very similar. So for example, if we have this like tertiary alcohol, we know tertiary and secondary both go via E1. If it had been secondary as well, it would have done the same thing. And you'd want to react it with some kind of strong acid. We talked about H2SO4 or this TSOH thing, right? And this would happen via two steps after this took on an H from the strong acid. It would be a good leaving group, it would leave, and then the elimination could go ahead and occur, and it can take a hydrogen. And what we end up with is, if this is our alpha carbon, either one of these can be our beta. We'll get something like this, and that would be our product. Just like when we were doing other E1 and E2, you can get a multitude of products. You can get the cis and trans, as well as major and minor products. So not too much has changed. The only thing to think about is during an E1 reaction, you can also have the alkyl halide, or not the alkyl halide, the alkyl shift, as well as the halide hydride shift. So let's talk about what that means. So if you have something like this, so here I have a secondary alcohol, and I go ahead and let's say I reacted it with a strong acid, so it would have taken on an H. This would have left, leaving us with this carbocation and a secondary position. And we know that it doesn't want that. This over here is quaternary, so what's going to happen is you'll have a whole methyl group shift over here. And then now the positive charge will be there. And now we can go ahead and do an elimination reaction. I'm shaving you all the extra stuff. Oh, and by the way, when this shifted over here, one of those methyl groups, so this methyl group right here, let me make it in blue, would have shifted over here. So now we can do an elimination reaction that's tetrasubstituted and very stable. And this would be the major product. Okay, there's another way that you can do elimination reactions, only done via E2, and it's with the following reactants. It's with pyridine and POCl3. So when we were doing a strong acid, or strong, oh, I realized I missed the primary right here. So if we also have a primary, that's gonna go via E2, by the way. So it's gonna be that one-step situation. So if we react it with a strong acid, again, it will take on the H, it will be a good leaving group, and then we can go ahead and do the elimination. You'll just get the standard that. So sorry, I forgot that. Okay, so generally primary with a strong acid is going to be E2, secondary or tertiary with strong acid is going to be E1. Again, there's a second way to do it via E2, and that's with pyridine and POCl3. So for POCl3, kind of looks like this. Got a phosphorus, double bonded to an oxygen, like this, okay? So if we take this hexanol, what's going to happen for this particular reaction, and remember the leaving group is going to have to leave, and then we're gonna, or at some point the leaving group will have to leave, and we'll have to have a hydrogen kind of let go of its bond and knock it off. So first things first, this will actually bond to this, and that will actually cause the Cl- to take off. Okay. So our very first reaction now, I'll draw down here, is that we now have this alcohol, but it has this huge group on it. That thing. Plus we have a Cl- just kind of chilling. Now we can go ahead and proceed via E2. If this is our alpha, we can choose a beta to be here or here. I'll choose it to be there. And then you would think that the chlorine comes in and grabs the hydrogen, but that is not the case. What happens is pyridine up here, which has this nice lone pair on the nitrogen, that's what actually will come in and grab the beta hydrogen. So I'll grab that, this will go there, and that can go up there. So it just knocks everything out. Okay, so you have essentially now this thing. We already accounted for a Cl. You'll also have this NH pyridine thing that would now have a positive charge on it. And then we also have the OPOCl2 negative. And that extra O was added when this thing took off here. Okay, let's see. Let's go ahead and keep going. So you can convert alcohols to something that we're used to, those alkyl halides, by reacting it with an HX. You can't just use an X minus. Remember, X minus is a good leaving group. It wants to leave. OH minus is a good nucleophile. So you can't just take an X minus and throw it in there. It's not going to cause this alcohol to come off. But if you have an HX, it can, because again, the alcohol can grab the hydrogen, and that makes it a better leaving group. And that's exactly what happens. So there's two different mechanisms that can occur. We already know them. One is via SN2, where after it grabs the hydrogen right here, it becomes this OH plus, and then it's pretty easy going. In one fell swoop, the nucleophile will hit this carbon here, and the leaving group will leave, and you're left with those two products. That occurs with primary. So with primary alcohols, you can have an SN2 reaction. With secondary and tertiary alcohols, that's when you're going to have the SN1 reaction. And actually during this, we can also even have the shifts. We can have a alkyl or hydride shifts. Just like with E1. And again, that's because you're left with a carbocation. That carbocation is going to find the most stable position possible before the nucleophile comes in. All right. So the reactivity of hydrogen halides, in other words, these acids here, is more reactive the bigger you get. That's because they're less stable together. They're happy to be pulled apart from each other. So HI is going to be a lot more reactive than HCl. In fact, HCl, if you have it on a primary alcohol, it actually requires some special conditions. And those special conditions are that you would add this zinc chloride to it, and it would occur via this reaction then. So if you need to put a Cl, which is less reactive, onto a primary, then you have to follow this reaction. All right, much like we're used to, with an SN2 mechanism, you're going to get the inversion product, but with an SN1, you'll get a racemic mixture. So let's go ahead and see if we can practice it without worrying too much about the mechanisms here. In this first reaction, I have HI, and I have what appears to be a primary alcohol. This D, remember, is just deuterium. It's a heavy hydrogen, but it still acts like hydrogen. So here we have an alcohol, here we have a hydrogen. So this alcohol is only attached to a carbon, attached to one carbon, so therefore it's primary. If it's primary, it's going to occur via SN2. And again, you'll get the inversion product. And we're just going to be replacing it with the alkyl halide, so I. So where an alcohol was before, now we have an I. With HBr, I'm not really sure why it's drawn this way. This is actually non-stereogenic because this is a mirror image right here. So these are both attached to the same thing. So you will actually only get one product. but this would occur via SN1. And you get something with a methyl and something with a bromine in it. And last but not least, here we have the secondary alcohol. So this was secondary. Here we have, oh, actually, excuse me, that was tertiary. Here we have a secondary alcohol. So with the secondary, again, it's going to occur via SN1. And we know this is actually a stereogenic center. So you're going to get the inversion product and the other product as well. So you'll get a racemic mixture here. And both of those would be in equal amounts. Again, that's because the alcohol will fall off first, leaving the carbocation, and the chloride can come and attack in any direction it wants. All right, now we talked about rearrangement can occur with SN, with E1, but it can also occur with SN1. So just to make sure that we understand, let's walk through this real quick. So the first step of this, I noticed that this is a secondary, and so I'm automatically thinking it's going to be SN1. SN1, after this grabs the hydrogen from the bromide, those electrons go back onto the bromide, and now you have a good leaving group, and that was the whole point of reacting it with a strong acid, is so that it can pick that up, and now it's going to be a positive charge thing. With an SN1 reaction, the leaving group leaves first, and once that leaving group leaves, now you're left with a carbocation right here. This is only secondary. It could be more stable if it went to tertiary. So that's exactly what it's going to do. You'll have a hydrogen here and a hydrogen here, which will move over there, therefore allowing this to occur. So you'll have a 1, 2 hydride shift. And now that that has occurred, now we can go back to this bromide, which is just kind of chilling, and it can go ahead and attack. And this is again why you get a racemic mixture if this had been a stereogenic center, because it could attack from here or it could attack from up there. Either way, you'll get that product in this case because it's not stereogenic. All right, let's do a little more practice. It says, what is the major product formed when each alcohol is treated with HCl? So let's treat each of these with HCl. Starting with the first one, I look at it, I say, hey, that's tertiary. This would proceed via SN1. Okay, remember, only if it's primary and we're trying to put a chlorine on there, then we need to do the zinc chloride. But in this case, it's tertiary, so we can proceed via SN1. It would do a lot of the stuff it did up here, minus a hydride shift because it's already tertiary. Oops, Br, not Cl, not bad. In this next case, hopefully you recognize there's a quaternary carbon here, adjacent to a secondary or something lower. So what that means is you're going to get a shift. Remember, a quaternary will actually lead to a methyl shift. So you're going to get something like this, where this whole methyl group right here shifted over to there in the middle of the process. Okay, some other random reactions. This is where things get a little bit crazy, because I'm just going to continually pile reactions on you. I have about, I don't know, 6 or so different reactions to start thinking about. They're still going to stick with the SN1, SN2 theme, but there's going to be several different reactants, and you do have to memorize these and know them and know what each one's for and know what each one does. Okay, so we talked about primary alcohols being difficult when you're adding chlorine, and we said you can add zinc chloride to it to do a primary SN2 reaction. Another option is SOCl2, and you can react it with pyridine. In that case, you can get a primary alkyl chloride. You can also do a secondary alkyl chloride via SN2 by reacting it with the same SOCl2 and pyridine. So pretty much if you're trying to put a Cl on some alcohol, it's a good safe bet to use SOCl2 and pyridine if it's primary or secondary. Then we have our any other alcohol, primary or secondary as well, and you're trying to put a bromide on it, you can use PBr3. If you use PBr3, again, you can do it via SN2 for secondary, even though normally you couldn't if you were doing HBr. So here we have a table that just generally summarizes some of these things. One of the main themes to look at is the fact that SN2 is pretty much always for secondary and tertiary, or excuse me, SN1 is always for secondary and tertiary, and SN2 is for primary and methanol. But don't forget that there are those exceptions where you can use SOCl2 for primary and secondary, and PBr3 for primary and secondary. They didn't include the zinc chloride on here, I'm surprised, but zinc chloride would work very similar to this one right here. Okay, let's practice, shall we? Okay, it says draw the organic products formed in each reaction and indicate the stereochemistry. So I see this and I know, remember this SOCl2, it allows a primary or secondary alcohol to go via SN2. So I have a primary, I know that this can work. I need to switch pens, I know it's hard to see that one. And so all we're gonna get is just a Cl. Okay? If this had been a stereogenic center, we would have gotten the inversion product because that's what SN2 does. In this next situation, we have what appears to be a tertiary alcohol. The tertiary alcohol is reacting with HI. We know HI is a great group. It's happy to break apart from H, and it's a good nucleophile for SN1. And so what we're going to get, because we know it's via SN1, also because it's tertiary, also the HI helps, is we are going to get both products for the racemic mixture. So my first one will be, I can draw it like this. I'm just going to replace the OH with an I, and we'll do the opposite. We'll have the I on the wedge and the methyl group on the dash. Next, I see this one. This is secondary. So for a secondary alcohol, normally I'd say this is going to be SN1, but I should recognize these two reactants, SOCl2 and PBr3, are going to work via SN2. And so in an SN2 reaction, hopefully remember that we'd get the inversion product like that. Okay, now we're moving on to even more reactions. We don't have time to stop because we got so many. Ethers with strong acid. So ether, if you remember, is an R group attached to an oxygen to another R group. If you react it with two equivalents of a strong alkyl acid, so HI, HCl, or HBr and HI, I guess HCl is not strong enough, you will end up with wherever the oxygen is on either side will be an X. It's probably easier to show you than to tell you via words. So let's do it. For example, if you were to treat in question A, this thing with 2 equivalents of HBr, you would get this first product. It would like split apart like that. And on one end would be a Br, and on the other end would be a Br. Now these happen to be the same 2 molecules, so really you could have written that you would have gotten 2 of those. And your other product would be water. You had 2 H's and it joined with that O. You could do the same thing with this one. 2 equivalents HBr. The first product would be this thing with a Br. So all I did was draw this part with a Br there, and I'll draw the other part with a Br there. And then plus water. So you can take an ether, react with HBr or HI, and this is what's going to happen. If you'd used an I, it would have been I. All right, we're going to talk about thiols and sulfides a little bit. Before we get into there, you should probably know what a thiol is. I believe we've talked about it briefly in our functional groups. But a thiol is some kind of R group to an S to an H. And a sulfide kind of looks like an ether, but it's an S. It's a sulfur instead of an ether. Naming them works a lot like alcohols. So it's very much like naming an alcohol. For example, remember with the alcohol, we put the "ol" at the end. Here we're just going to put a thiol at the end. So if you're counting carbons, 1, 2, 3, 4, 5, doesn't matter which end you start with, the thiol always gets the priority. In this case, it happens to just be 1. So this is some kind of pentane, but we only write pentane 3 thiol. Okay. Very much like alcohols. On this next one, if you go to find the longest chain, it's already found it for you. You want to put the lowest number on the thiol. So you wouldn't want to start over here, you'd want to start over here. 1, 2, 3, 4, 5, 6. On the 4, it appears I have a methyl group. And on the 2, I have the thiol. This was a hexane, so I would call it first a hexane, and then 2 thiol. Again, if you have alcohol naming down, this should come almost naturally now. Just like with alcohol, you're going to put your 1 will always be the thiol, and so you don't need to write a 1 if it happens to be on a 1. It's just cyclohexane thiol. But on the 2, we have a methyl, so that's why this is 2-methyl cyclohexane thiol. So you can make a thiol by reacting something with SH negative. It's going to be via an SN2 reaction because SH negative is a good nucleophile. Okay, so it'll proceed via an SN2 reaction, meaning if you had a racemic, you'd get the inversion. So let's go ahead and practice that. So you can see right here, it comes in, the bromide leaves. It's actually a relatively straightforward preparation process. But once you've prepped it, let's talk about what you can do. You can put them together and make a di sulfide. So you can do that using Br2 or I2. We're not getting into the mechanism, but you would have 2 HBRs left over, or 2, yeah, I'll just say 2 HBRs in this particular reaction if you reacted with Br2. I guess I really don't need to draw anything. It's already been drawn for you. So essentially it took this and it paired it up with another one. And then over here, it did the opposite, it broke it down. You can break it down by using zinc and hydrochloric acid. Okay, so let's go ahead and practice these on the next page. So in this first one, we have this sodium thiol. Remember, this we can get rid of. Now, boom, we got a really good, strong nucleophile. We know with a strong nucleophile, this is going to, again, go via SN2. So essentially, the nucleophile just, boop, pops up in there, chlorine goes away, and you know that it's going to be a backside attack. So that deuterium is now going to be on a dash. So this was just a straightforward replacement. Br2, if you remember the Br2, or I2, what they do is they join two thiols together. So we'd want to react two of those plus Br2, and what you'd get is a miserable thing to draw with a really heavy pen. So first, you'd get that. You would have the S, and then you take the same thing, and just imagine if I'd flipped it around. The only interesting part is that you flipped it around, but when you flipped it around, it also had a backside attack. So what was a wedge here, or what was a wedge here when you flipped it around, will remain a wedge. So you get that. To that, I believe. So you can imagine flipping it up, flipping it around, and that's how you get this. Okay, last but not least, hopefully you remember zinc and HCl from the previous page. Zinc and HCl breaks things apart. And this is a lot more fun to do, I think. You have one of these. It goes to an S, to an H. And this one would be the exact same product. You just break it apart, add an H to each side. So you would end up with two of those. All right. Wow, what I thought was going to be a really long lecture is turning out okay. So let's keep going. Let's talk about epoxides. We talked briefly about them in the last lecture. I think I gave you a pretty similar picture to this. And there's just a couple things to note here that we're going to encounter. In this case, you have a strong nucleophile. Where it's going to attack will actually depend. It says backside attack on this one. That's because you have, again, a strong nucleophile, and it's going to be SN2. So this comes in, it pops these electrons up, so you get this thing right here. Now, the one thing that we haven't covered much of, hopefully you can kind of see what happens, is that you have an H. Oh, H. And this would grab that, and that would go like that. So that's how you end up with the OH. So generally you'll see a step 1 where it's going to be some sort of nucleophile, and step 2 is going to be water, just to ensure that you know that you got an OH there. So we're going to prepare some alcohols using epoxides. Okay. And an unsymmetrical epoxide, if you have a nucleophile, a good strong nucleophile, it's going to attack the less substituted carbon. So in this case, you can see hopefully that you have, here you have a quaternary carbon, and here you have a secondary carbon. So it's going to attack the secondary carbon simply because there's just more space for the nucleophile to get in there. When it attacks, the electrons from here have to go up to the oxygen, so the oxygen is going to end up on the other side of the nucleophile. There, you can treat it again with water, and you get the OH. Let's practice. Okay, it's kind of fun stuff. Okay, so here we have a strong nucleophile, so we know that it's going to attack the less substituted side. So it's going to come in here, whoop, and attack that. These electrons then have to go up here. So once again, you're going to get the oxygen on the opposite side. So we'll have something like this. This will be an O, CH2, CH3. Now, because this is happening via SN2, this will become a dash. You're going to have the inversion product. It's going to be a backside attack right there. It can't go like right in front of the oxygen, which is pointed toward it. Nothing else changes though. On this side, it remains the same. You have that methyl group, and you have the oxygen, but don't forget you treated it with water, so really you have an OH. We'll do the same thing here. All right, we have a strong nucleophile. So it's going to come in and attack like that. This is the less substituted side, that's why it attacked that. This is the more substituted side. What that's going to do is it's going to cause these electrons to go up here to the oxygen. So now you have this oxygen here, down to a carbon, over to another carbon, down to this carbon, which is triple bonded, to another carbon, to a hydrogen. And then we can't forget that we had this methyl group and the hydrogen. Those haven't changed. Then when we treat it with water, this would have had a negative charge, but now it has an H on it. And that would be your final product. You could, if you want to, though it wouldn't be a stereogenic center, you could draw the H's like that. All right, now let's look at another thing that's going to throw everything off. Strong acids also work, but the difference with strong acids is they're going to attack the more substituted carbon. And hopefully we can make some sense of why that is. HBr is actually that, right? And the first step here would be the oxygen would attack the hydrogen, and that's what allows it to kind of separate. So it actually separates first before the attack. Okay. So in this case, once this happened, it's kind of interesting how they did it, but in this case, once that happened, it broke apart, and you can count these carbons 1, 2, 1, 2. Okay, the Br came in and attacked the less substituted side over here because the oxygen ended up going up over here. But we'll do some problems here in a second to make sure you're comfortable with that. Again, because this is now SN1, we're going to get the enantiomer products as well. So the first thing that's going to happen is it's going to separate, in other words, like the leaving group, and in some ways leaves before the reaction occurs. So this occurs with whenever you have a HZ or even a neutral nucleophile, as long as you have acid. That will occur, or you get the more substituted carbon attacking. Let's do an example here. 2 examples, and make sure we're comfortable with both of these. And the first example, I'm using HBr. Do you remember HBr? That means more substituted. It's going to attack the more substituted one. So I'll show you what we'll end up with, and then let's break it down and understand why. So if it's going to attack the more substituted one, we get this. By more substituted, I mean this is the tertiary. It's tertiary, and this one's secondary. If we'd had a strong nucleophile, it would have attacked over here. But why is a fantastic question. So remember, the first step is that this is going to grab an H. So in step number 1, let me go ahead and just rewrite it up here. So the oxygen is going to attack an H. Bromide goes over there. That causes us to now have an H on our epoxide. Now, oh, and I should draw it like this, sorry. The stereo center hasn't changed. Okay, but now you have this Br negative coming in. It was a product from over here. So that Br negative has a couple choices. But if you look, and the reason this acts like an SN1 reaction is kind of weird, but the reason it acts like an SN1 reaction is because this oxygen is electronegative, right? So it's pulling electrons toward it, and this one's pulling electrons toward it. This has a partial positive charge on it, and this one does as well. I want to write smaller, so I'm going to use a pen. This carbon right here also has a partial positive, but my question to you is, which partial positive is more stable? Hopefully you agree that this one is the more stable partial positive, and because this one's the more stable one, that's why the Br is going to come in and attack. And in the other situation with the nucleophile, I didn't care about stability, it was just attacking. Here, we actually have a situation where it's more stable there, and therefore the bromide is going to go and attack on that side, causing these electrons to go up here, by the way, and push off. And so that's why you end up with, well, that's why you end up with that. Okay. And this had to be a backside attack because it couldn't go in the way of this OH. So it flipped, the methyl group is now on a wedge and the bromine's on the dash. All right, in this situation, we have a strong nucleophile. So it's going to be the less substituted one. More substituted again was because it was an HX. Less substituted is it's got a strong nucleophile. So when you go to draw the product of this, it's going to be relatively straightforward. You pretty much just redraw the whole thing. You know you're reacting with water, so we'll have an OH here. The less substituted carbon, this was tertiary, this is secondary, the less substituted carbon is here, and that's the one where the nucleophile is going to attach, and we're going to get the inversion of that. All right, so I hope that helped. And I'm looking around to see if there's anything I didn't cover. I think we're good. So anyways, let me know if you got questions. If you do, well, we'll cover them in class, or just email me. All right, have a great day. Bye, y'all.